When learning how to manage the permissions for files and directories in the file system, one main command comes to mind. The command chmod is used to change the mode or permission bits for any given file or directory. It's called change mode because we refer to the permission expression that we've seen previously with the 3 groups of 3 as the mode bits of a particular file. When we change the mode, we're referring to changing the mode bits or permission bits set on each file and directory. There's a few ways we can use the chmod command in order to change the permissions on a file or directory. First, there's the concept of changing permissions with the symbolic method. When we use the symbolic method, we use the letters U, G, and O for the user, group, and other permissions. We also have shorthand for A or all when we need to change all these bits at the same time. We then use the plus, minus, and equals to either add, remove, or exactly specify the permissions we wish to enable. And lastly, we use R, W, and X, the read, write, and execute permissions we recently reviewed. When we wish to use the symbolic method of permission management and the chmod command to do so, we combined the UGOA, the symbol of plus, minus, and equals, and the permissions RW and X as fit for the files we wish to manage. A properly formed command would take the form shown here. We would start with the chmod command, name what we wish to alter in the permission form using the syntax who, what, and which. Who corresponding to the user, group, other, or all. What corresponding to adding, removing, or exactly setting the permissions that are which are W and X, read, write, and execute. In that fashion, we can begin to form permission statements that look something like the following. In our first example, we're using a chmod statement. Let's dissect this statement to understand exactly what's going on in the permissions here. We're using chmod to change the mode bits for group and other, G for group, O for other. A minus sign means that we're removing permissions, R and W, read and write, for the file 1. In this case, read and write access to file 1 for the group members as well as all others would be removed. In the next example, we're adding execution permissions for everyone on file 2. In this way, we'll use the chmod key A to say for all, group, user, and other. We're going to use the plus symbol for an additional permission, and we're going to add the execute permission to everyone. This means that everyone should have execute privileges for the file specified, file 2. That's the first way that we can manage our permissions, but there's also a numerical way to manage our permissions. When we start learning numerical work with our permissions, we need to understand how to express the 3 values for R, W, and X bits being set on and off in an octal expression. Let's start with a quick look at what binary and octal representation means in this case. Let's go ahead and start working with our permissions and assigning them numerical values. Let's start by understanding we have users, group, and other. Each of these will receive one or more of the 3 permissions: read, write, and execute. We'll go ahead and draw a little line here and a line here to collect our work. Now, let's start trying to iterate what some of these would look like. If we want our user to have read and write permissions, our group to have read permissions, and no one else to have permissions, we could fill out the graph as such and express the resulting permission as R, W, dash. For group, we would have R, dash, dash. And since the other has 0 permissions, it would be 3 dash. It's in this fashion that we can begin understanding the binary then octal representation of these particular permissions. I'm going to draw a line between user and group and other. Here we now have begun to start understanding that we have 3 sets of 3. I'll now convert each one to a 1 where they have the permission or a 0 where they do not. I'll use a separate color to make sure we can keep our work separate. Here we have a 1 because the read bit is enabled, a 1 where the write bit is enabled, and a 0 where the execute bit is not enabled. Here we have a 1 for the read bit and a 0 for the other bits. Lastly, we have none of these permissions for other, so therefore we have 3 zeros. So that we can keep this straight, I'll go ahead and label at the top that this is user, group, and other. At this point, we've taken our intended setup of permissions for user, group, and other corresponding to the read, write, and execute permissions, written them out as we would see them on the displayed permissions output of an ls-l command, and now converted them to on and off switches in the form of binary. Now, binary math is not native to everyone. However, this is where we get the translation from our binary to what is known as octal representation. Binary has 2 digits, 0 and 1, while octal has 8 digits, 0 through 7. We can go ahead and refer to binary to octal conversions to understand that 110 in binary is actually a different number, a single digit in octal. That digit in octal is 6. 100 in binary is expressed in octal as 4. And 000 in binary is the same single digit 0 in octal. If binary or octal conversions are new to you, take some time and get to know these. They can certainly provide value when you're converting these permissions. But know that if it's providing challenge or it is too new to you and you still wish to take time to learn this, you'll always be able to express your permissions using the symbolic representation we talked about previously.